This is Dr. Pratima back with you with Schrodinger equation for one-dimensional problems, taking a particle in a potential box. This is a continuation of my previous lecture where we have derived the Schrodinger equation. In the Schrodinger equation, at the end of the applications, I have told you that Schrodinger equation, when applied to any particular subatomic particle, you can predict its behavior and you can even explain the matter taking that prediction of the behavior. So we apply taking one condition of a particle and applying the Schrodinger equation, we try to understand the behavior of the particle in this video lecture. So here we are considering a free electron in a metallic crystal experiencing a potential barrier. Why will an electron experience a potential barrier? In a metal, there will be positive ion lattices. So the free electron, though it has free behavior and thus is a reason for the enhancement of the conductivity of the metals, it still has experiences potential at the ion lattices. So we are now taking this condition of the electron where it experiences a barrier in its potential. And thus we are considering a box of width L. So if I'm considering only in one direction, x, then I can take the limits as x is equal to 0 and x is equal to L when the width is L. The same, no, if you take 3 centimeters width box, when you take a scale, the starting will be 0 and the ending will be 3. So this is the same condition, and let me take an electron. So now to understand this electron, it's very difficult. That's what Heisenberg says. So there is a lot of uncertainty in understanding this electron. You know very well that it is a subatomic particle. So in order to understand this electron, we have to definitely take the Schrodinger equation, but that alone cannot happen unless you take some assumptions. What are the assumptions? Let us consider that this electron is restricted by the sides of the walls. Okay, you don't take the electron to be free throughout, and that's why you are enclosing it in a box, and hence you call it as a restriction by the sides of the walls. And now I just want to tell you one thing. Just imagine a box, open the lid and cut off the lid, and just you keep on enhancing the sides to an infinite level. What can you call that? If you take a round box, just like how you get for a watch, okay, then you can take it as, you can picturize it like a well. So here you are studying the potential of the electron, hence you call it as a potential well, and increase the height from minus infinity and infinity. If you want to take on either sides, you can even consider it as minus infinity and plus infinity also. And what about the potential? If you want to understand the potential of the electron, it's really impossible. So let me consider that the electron moves only in the x direction with elastic collisions with the walls. What is elastic collision? If I pull an elastic like a string or anything like a rubber band or anything, then if I leave, again it will be coming back. That means there is no loss of energy for the rubber band. So the same way here, the electron also is moving, but it will just go, and when it hits the wall, it's neither taking any energy nor losing any energy. So you call it as a elastic collision. So it's just going and coming back. So when I understand it in terms of the existence of the electron, when I understand it with respect to the elasticity, then I should take that the electron is not existing there. So psi of x is equal to 0 here. The same here. So psi of x equal to 0. So psi of x will help you to understand why are you taking psi of x. Psi of x is always an entity which helps you to understand any particle with respect to its momentum, maybe its velocity, maybe with respect to space and time. So here you are saying that it's an elastic collision. So there is, you have to consider that it just goes and come back. So though physically the electron will be there in the box, at the walls it's not there. Okay, that's what you have to understand here. And the potential inside the box is 0. So V is equal to 0, whereas throughout the length of the box, and outside it is infinity. That's what it is given as infinity. So with these conditions, holding on to these conditions, let us take a next step by considering the Schrodinger wave equation. What is the Schrodinger wave equation, which we have proved in the previous lecture, which you can find it in the description box? D square psi by dx square plus 2m by h bar square into E minus V into psi equal to 0. So, if I consider this condition where the potential of the electron inside the box is 0 and psi is given in terms of the x direction, so as we take it as psi of x. So substituting these conditions in this Schrodinger equation, what do I get? D square psi by dx square plus 2m by h bar square, V is equal to 0. You are left over with only E in the numerator. So 2m E by h bar square into psi equal to 0. And k, the wave vector, can be written in terms of E as k square is equal to 2me by h bar square. So just take it, and this will play a very eminent role in understanding the, or even I can say quantizing the energies of the electron later at the end point. So now you have a second order differential equation. And your mathematics students, you know very well that you can go for the general solution of it. So how can you go for the general solution of it? You get it in terms of psi of x. So psi of x is equal to a sin kx plus b cos kx. Now you have to solve for this general solution to get the values of a and b. How can you get the values of a and b? You have a nice tip here. What is the tip here? You have the understanding of the picture. What is the understanding of the picture? You have the limits, the boundaries. X is equal to 0, x is equal to L. What is it? X is equal to 0 and x is equal to L. You have the predictions of the LHS. Psi of x equal to 0 and psi of x equal to 0 here also. So this you take it as boundary condition A, this you take it as boundary condition B, and move ahead. So this is the boundary condition A and this is the boundary condition B. Now what is the procedure you have to go? You have psi of x is equal to a into sin kx plus b into cos kx. So substitute first the boundary condition A. Listen carefully. First you have to substitute boundary condition A. When you substitute boundary condition A, you will get some result. Take that result, come back to this equation number 2. That means come back means you substitute that result in equation number 2. Whatever you get, take that and apply the next boundary condition. That's the way you have to follow. Okay, I repeat once again. You have a solution here. Psi of x is equal to a sin kx plus b cos kx. You have two boundary conditions. First, take the first boundary condition, apply it on equation number 2. You will arrive at some result. Take that result and substitute it again in equation number 2. You may get equation number 3. Okay, take the 3 and substitute that boundary condition 2 in the equation number 3. But here, I have given it as equation number 4. So let's see how it goes. So first here, if I substitute boundary condition A, substituting the boundary condition A onto this equation number 2, what will I get? Psi of x equal to 0 equal to A into sin k0 means 0 plus B into cos k0 means 0. What is 0 equal to A into sin 0 is 0. Plus B into cos 0 is B. So B equal to 0. This is the result you got when I applied the boundary condition A. That is the first boundary condition. What did I say? Substitute this result in equation number 2. So what will I get now? Psi of x is equal to A into sin kx. This is what I got. That is what here you got it as equation number 4. Now use the boundary condition 2, that is B. What is the boundary condition 2? Psi of x equal to 0 at x is equal to L. Substitute these values here. What do you get? Psi of x equal to 0. So the LHS becomes 0 is equal to A into sin k. What is x? X is L. So now let us look in taking the algebraic concept here. If AB equal to 0, either A should be equal to 0 or B should be equal to 0. If A is equal to 0, if A is equal to 0, then what does it mean? Psi should be equal to 0 everywhere, right? Why? Because A represents the amplitude. That means you are saying that the particle isn't there. So whatever your issue is, you started with an assumption that itself it's getting nullified. So you should not take A equal to 0. If A is not equal to 0, then B should be equal to 0. What is B here? Sin KL. So sin KL equal to 0. If sine KL equal to 0, you know, according to the trigonometric things, KL is equal to n pi, where n is equal to 1, 2, 3, and so on. So at last you got K is equal to n pi by L. Taking this into your hand, move on to the next. You have two supports here. Substitute this support in this. You have now a quite well-defined form of psi of x. What is it? It is a into sine of n pi x by L. Holding on this psi, I am trying to get still more, I can say, information about the electron. So for that, I want to differentiate it once with respect to x. So what do you get? Differentiation d by dx of sine nx is n into cos nx, right? So I just substitute that here, where n is what? N pi by L. So you get this. Differentiate it once again. So cos is what? Minus sine. And n is already there, and you get another n. So n into n is n square. What is n here? N square pi square by L square. So you get this. Continuing ahead. What is there here? A into sine. This term, I can take it as this. This is the same RHS. What is it? You can substitute as LHS, right? So minus n square pi square by L square is here, and the rest of the circled one, I can take it from equation number 6. So now you got the Schrodinger equation in a bit nourished way. Okay, d square psi by dx square plus n square pi square by L square into psi equal to 0. From K, you now got it in terms of the potential box. Let's move on. So comparing, what did you do now? Let me just try to recollect for you so that you'll not feel confused. First, we started with the Schrodinger equation d square psi by dx square plus 2m by h bar square into e minus v into psi of x equal to 0. And we assumed that v equal to 0 inside. So d square psi by dx square plus 2m by h bar square into e psi of x equal to 0. And this we considered as k square. So you get it as d square psi by dx square plus k square into psi of x equal to 0. What is k square here? If you recollect, 2me by h bar square. But what is k now for you? It is n square pi square by L square from my previous slide. So now taking this condition, I want to get this E, so that I can quantize the energies of the particles as it moves along the height and the width of the potential box. Let's see. Simple algebra. You can get it as n square pi square into h bar square by 2m into L square. Take h bar is equal to h by 2 pi. Then you will end up as en is equal to n square h square by 8m L square. So here you should understand one thing, that the energy of the particle cannot take just any values, but it is a discrete set of energy values. It is a set of energy values which is very discrete, and you can quantize them according to the principal number by taking n is equal to 1, n is equal to 2, n is equal to 3, and so on. Okay, I'll describe this in another 2 slides ahead, more the depth of it. Okay, now still I am not satisfied with psi, because I am still having A. What is this A? In order to get this A, I apply the tool of normalization condition. In my previous lecture, I have told you that what is normalization condition. In a particular, maybe I take a space or like a big volume of X. In that, I take a small finite volume dx, and in this finite volume dx, I want to study the electron's behavior. Then I can take the psi square dx equal to 1, even if it is 3 dimensions, psi square dx dy dz equal to 1. 1 means I am predicting as if I'm taking as if that the particle is existing in this solid volume of dx. I'm taking it as that it is existing. If it's 0, it's not existing. So, and if I have any limit, well and good. I have the limit here as 0 to L. And if it is dy, then I have another limit. If it is dz, I need another limit. But now we are taking only x direction, so one limit with 0 to L. And I have psi of x, just substitute psi of x. with k is equal to n pi by L. Okay, so now you have this, just go for the integration. Go for the integration, then you get 1 minus cos 2x by 2. Take 1 by 2 outside and take it under the a square by 2 and apply the limits from 0 to L and equate it to 1. We know how to apply the limit. First apply the upper limit and minus lower limit. So if you get a square by 2 into L equal to 1, so you get a as a square is equal to 2 by L. So a is equal to under root of 2 by L. Take this 2 by L and substitute it here. Then you get a very normalized wave function now because you applied the normalization condition. So psi n is equal to 2 under root of 2 by L sine n pi x well. You may ask, what is so great, ma'am? Yes, if you substitute for different values of n, you can get different values of psi. So what? You can assume, you can describe the behavior by taking psi for different values of 1, 2, and 3. See here, there is maximum and on either sides it is nullified. Okay, and in the halves it is maximum and even negatives. Okay, and here as a fraction values. Okay, so now you got like predicting what is the nature of the particle, right? Till then there was no weapon for the physicists to understand the particle's behavior, and this is a very great achievement. Okay, so now still I want to find the location of the particle, like how much probability is there for me to find at what position throughout the width of the potential box. So for that I am taking this probability. We know according to Bond's approximation, you can take it as mod psi n square dx. Okay, so mod psi n square dx, I have psi n, just substitute it, and if this has to be equal to 1, that's what the probability should be equal to 1 to locate the particle. Then n pi x by L should be equal to pi by 2, 3 by 2, and 5 pi by 2 according to trigonometric values. Okay, so from that I can take x as, yes, for suppose for people who can't understand, let me do 1. N pi x by L is equal to pi by 2. Pi and pi gets cancelled. So you get x is equal to L by 2n. So that is for first, next this, next this. So for n is equal to 1, the maximum probability is this. For n is equal to 2, if I substitute, what will I get? 2 pi x by L is equal to pi by 2. If I take the first one. Okay. So then what will I have? X is equal to L by 4. So the same way, if you take x is equal to 2 for the next value, you get 3L by 4. You can just do it a simple algebra. So what does this really help you to understand? Let's see here. See, for n is equal to 1, before taking n is equal to 1, let me take n is equal to 0. What will happen? En. If I take n square h square by 8m L square. If n is equal to 0, energy of the particle is 0. Energy of the particle is 0 means there is no particle. But that's not what we have taken. So there is no n is equal to 0 level actually. So n is equal to 0 level is not at all there. The first level is the n is equal to 1. And the first excited state will be n is equal to 2. Okay. So that's what you have to understand here. And yes. N is equal to 1, the maximum probability is at L by 2. So if this is L and this will be half, right? So what the maximum probability it has risen here and then it is decreasing. And on either side the particle is, that's what you told psi of x equal to 0. Now you can see it in a picturized concept. Okay, so now and L is equal to here in half. So it is L by 4. And then this will be 3L by 4, right? This will be 3L by 4 and so on. This is for this. This for this. So now you are able to find out. You can say, where is the particle at the lowest energy? Oh, maybe it can be here. There is much probability for the particle to exist in half of the potential box. You can very nicely explain. Okay. So this is an achievement of where you are able to quantize the energies here, as well as you are also able to find out the probability of the existence of the particle here. Okay, moving ahead, what are the achievements here? The number of nodes or the places where the particle have zero probability is located. Yes, this is zero, this is zero, this is zero, this is zero, this is zero. These are zeros, right? You're able to locate it, and you're also able to see that these are increasing with increasing energies. Yes, I have told you, if En is equal to n square h square by 8m L square, then E1 will be h square by 8m L square, and E2 will be 4 into h square by 8m L square. So E2 will be 4 times of E1. Yes, because h square by 8m L square is E1. So that's why here it is given as 4. Okay, so for E2, it is 4 times of E1. E1 is h square by 8m L square. That's what you have to understand this picture. Okay, so now what are you seeing with the increase in the energy? This is energy bar. Okay, so this is energy bar. So with the energy bar, you are seeing that the number of nodes where the zero probability is there is increasing. Here it is 2, whereas here it is 3, whereas here it is 1, 2, 3, 4. Like that, it is increasing. That's what this point means. And then as the energy of the particle becomes greater, the energy levels get closer together and overlap. Here it is wide, whereas here it is getting close, close, close as you go up, forming a continuum of the energy states. So, and then this continuum means what? The particle is getting free and can have any energy value. And at such high energies, we can say that the classical mechanical model is applied as the particle moves just like a continuous wave. So you started with an electron and you ended up at a continuum state where the particle is executing a wave behavior. Thus, even using this Schrodinger wave equation, predicting some conditions, you arrived at the quantizing of the energy levels, the picturization of the wave function, and the proving mathematically and picturistically that the wave and the particles are exhibiting dually one in another as wave-particle duality. Hope you have followed me. Meet you in the next class.
Like, share and subscribe. Hit the bell icon for more updates.